This video will give examples with logarithmic functions. Convert to logarithmic form. 5 to the x equals 125. So in logarithmic form, this would be log base 5 of 125 equals x. And to convert log to exponential form, we'll take our base down here, raise it to whatever power is over here, and that will equal x. So 3 to the 10th equals x. Simplify. 5 to the power of log base 5 of 28. So this part is asking, 5 to the power of what is 28? And then we want to take that number and raise 5 to it. So in the end, by the inverse rule of logs, we'll end up with just 28. For here, we have 3.4, and we're asking with the log. 3.4 to the power of what gives us 3.4 to the power of 4.2. And so again, by the inverse power of logs, we end up with 4.2 as our answer. Solve. Log base 1/8 a equals 2/3. So we can begin by putting this into exponential form. So 1/8 to the power of 2/3 equals a. So now 1/8 to the power of 1/3 is equal to 1/2, and so that means if we want to raise 1/8 to the 2/3, then we'll have to square 1/2. So in the end, we end up with a equals 1/2 squared, or a equals 1/4. Log base 5 of a plus 4 is less than 2. First thing we have to check with logs is that this part is greater than 0. So our first condition is that a plus 4 must be greater than 0, or a is greater than -4. And then we'll actually solve our inequality. So one way we can do this is by raising 5 to the power of both sides. So 5 to the power of log base 5, a plus 4, is less than 5 to the power of 2. So then, using the inverse property of logs, we get that the right side simplifies to a plus 4. Then that means this is less than 25. So a is less than 21. And taken in conjunction with our first condition, which is that a is greater than -4, we end up with a final answer of a is between -4 and 21. Solve. Log base 5 of x plus 2 is greater than log base 5 of x squared. So again, our first conditions with these logarithms is that the thing we're taking a log of must be greater than 0. So we have x plus 2 is greater than 0, and x squared is greater than 0, meaning x is greater than -2, and the square of any number is greater than 0, so that doesn't limit us. Okay, so now we're going to take 5 and raise it to the power of both sides. So we end up with 5 to the power log base 5 x plus 2 is greater than 5 to the power log base 5 x squared. And so now we can get rid of the logs and the exponents because they'll cancel each other out. And we end up with x plus 2 is greater than x squared, or 0 is greater than x squared minus x minus 2. Now if we recall how to solve inequalities with quadratics, we can factor our equation, x minus 2, x plus 1. I'm going to put the 0 on the other side, so less than 0. And we can have our little number line. We have 2 and a -1. And we know that at these 2 points, our value is equal to 0. And so we'll test things that are less than negative 1. So let's just say I'll plug in negative 2 into my equation, x minus 2x plus 1, and I end up with negative 4 times negative 1, or 4. So this side over here is positive. If I plug in 0, I end up with 0 minus 2 times 0 plus 1, or negative 2 times 1, which is a negative number. And then if I try something greater than 2, let's say 3 minus 2 times 3 plus 1, 1 times 4, that equals 4. So this is positive. So therefore, when we were looking for cases where x minus 2 times x plus 1 is less than 0, we want the range from negative 1 to 2. So that means negative 1, x is between negative 1 and 2. And then recalling our initial condition was that x has to be greater than negative 2. But if we consider this interval, we see that that already fulfills our first condition, because anything that is greater than negative 1 will naturally be greater than negative 2. So we can just say that this is our final answer.